For many years, physicists believed that the universe began with an infinitely dense concentration of matter. This mass exploded in a dramatic event that led to the formation of atoms, molecules, stars, and galaxies, the structures we observe in the cosmos today. This explanation, known as the Big Bang Theory, has been the dominant model for decades. However, recent research has offered a fresh perspective, challenging the traditional view of the universe's origin. Instead of a single beginning, some scientists now propose that the universe is part of a cyclical process, one that includes endless cycles of expansion and contraction. This theory suggests that the cosmos may not have a true beginning or end, but rather exists in an eternal loop. Renowned physicist Brian Cox has also expressed skepticism about the Big Bang Theory, pointing out the philosophical and scientific dilemma of something arising from nothing. His doubts add an intriguing layer to the ongoing debate. Meanwhile, new findings from the James Webb Space Telescope further question the notion that the Big Bang marked the absolute beginning of everything. So, if the Big Bang wasn't truly the beginning, what came before it? Join us as we journey through the origins of the cosmos, exploring bold new theories, cosmic mysteries, and the frontiers of science. Don't forget to subscribe to our channel, like this video, share it with others, and hit the notification bell to stay updated on groundbreaking discoveries about the universe. The Big Bang Theory still provides the most detailed and consistent model of the universe's early stages. According to this framework, around 13.8 billion years ago, the universe was incredibly hot, dense, and compact, possibly as small as a peach, with temperatures exceeding 250 degrees. Within minutes, the fundamental elements of our world were forged. Observational evidence supports this theory, from the cosmic microwave background radiation to the abundance of light elements like hydrogen and helium. These findings match the predictions of the Big Bang with remarkable accuracy. For now, this remains the best description of our universe's development. Yet, despite its success, the Big Bang Theory has its limitations. It does not fully explain what happened in the very first moments, just before and at the supposed beginning. This is largely due to the constraints of current physics. The blend of general relativity and high-energy particle physics provides a strong foundation, but as we probe deeper into the earliest fractions of a second, the mathematics becomes too complex and our tools fall short. A key issue is the concept of singularity, a point of infinite density that defies logic and suggests the universe began from an incomprehensibly small and dense state. To resolve this paradox, scientists are turning to new frontiers in physics. One such approach is string theory. String theory aims to unify gravity with the other fundamental forces of nature, especially under extreme conditions. It introduces the idea of an ekpyrotic universe, from the Greek word for conflagration or cosmic fire, proposing that what we perceive as the Big Bang might have been triggered by a previous cosmic event, not the absolute beginning. This concept paves the way for cyclic cosmology, a theory suggesting that the universe continually undergoes cycles of birth, death, and rebirth. In this view, the Big Bang is simply a phase in an ongoing cosmic rhythm, not the origin of everything. As our understanding evolves, so does the mystery. Was there truly a beginning? Or is the universe eternal? Stay with us as we explore these questions and uncover what might lie beyond the Big Bang. The universe has long been a subject of contemplation, and string theory offers a robust mathematical foundation for such reflections. Within the framework of cyclic cosmology, the universe is seen as eternally oscillating between massive explosions, big bangs, and gravitational collapses, forming an infinite loop stretching both backward and forward in time. This compelling concept was proposed by renowned physicist and Nobel laureate Roger Penrose. He was fascinated by a striking mathematical parallel between the universe's extremely dense, hot, and compact state during the Big Bang and its future state, vast, cold, and nearly empty. Penrose's theory suggests that when these two extremes are pushed to their limits, they become mathematically indistinguishable. Paradoxically, a universe devoid of matter might be the very condition that gives rise to all the matter we observe. From this perspective, the Big Bang could originate from what is left after all matter has been absorbed by black holes, and those black holes eventually evaporate, leaving behind a sparse spray of photons in an empty cosmic void. In essence, the universe could emerge from near nothingness, though this nothingness is still a kind of something, an almost entirely empty physical universe. The true enigma lies in how the same state can be interpreted as both a cold, empty universe and a hot, dense one, depending on perspective. The bridge between these two extremes is found in a complex mathematical process known as conformal transformation, a geometric tool that alters scale but preserves shape. Penrose demonstrated that by applying such a transformation, the spatial and temporal structures of the cold, expanded universe and the hot, compact universe can be aligned. Under these extreme physical conditions, the notion of size itself becomes irrelevant, allowing the two states to be treated as equivalent despite their apparent differences. In the cyclic model, one universe ends in a cold, empty state, which then transitions, via conformal transformation, into the next cycle's hot, dense beginning. However, this transformation doesn't follow a conventional temporal sequence. Time and scale lose their usual meanings in these boundary states, placing them on separate timelines. For an observer within such a framework, the cold, empty universe would seem to persist endlessly. This intersection of physics and philosophy reveals deep questions at the heart of cyclic cosmology. While the physical model offers detailed mechanisms for how cycles might arise and evolve, it leaves open a more profound question. Why do these cycles exist at all? Why is there something rather than nothing? This is a fundamental metaphysical inquiry. For the purpose of scientific exploration, we focus on three main possibilities concerning the origin of these cycles. There may be no physical explanation at all. The cycles simply are. There could be an infinite chain of universes, each cycle giving rise to the next through some inherited quantum properties. There may be a single self-contained cycle, where the beginning of a universe is determined by some feature of its own end. These scenarios are appealing because they avoid invoking uncaused events and instead offer coherent models grounded in physics. Penrose, drawing on his interpretation of quantum mechanics, proposes an eternal succession of universes. In quantum theory, a system exists in multiple states simultaneously until it is observed, causing a random collapse into a single outcome. Penrose suggests that the transitions between cosmic cycles are shaped by such quantum randomness, with each universe bearing the unique imprint of probabilistic quantum events from its predecessor. Variations between cosmic cycles present exciting opportunities for experimental physicists. They hint at the potential to detect subtle anomalies or remnants in the afterglow of the Big Bang. What are your thoughts? Share them in the comments below. If you enjoyed the video, don't forget to like, subscribe, and share it to help more people discover this content.